So now we have the task of evaluating the mean distance r bar for a given probability distribution, right? That's kind of straightforward. We have an interpretation. The interpretation is that there is a linear city. It starts at the origin. It goes out till a finite radius capital R, right? And we just want to understand what is mean distance, right? So what is the mean distance of, at which a marker, location marker will be found going out from the, origin, right? So we want the first moment R bar, right? So we have a probability PR that we know we are going to be able to, see a location marker, observe a location marker, and this is given as k to the power k e to the power minus lambda r, and k we have now evaluated as lambda over 1 minus exponential to the power minus lambda capital R, so times e to the power minus lambda small r. So okay, let's move forward. So we have R bar, which is given as something we are very well aware of, 0 to R, small r, PR, dr, right? And I have, I'm going to write down, PR lambda e to the power minus lambda small r over 1 minus e to the power minus lambda capital R dr. I'm going to take everything that is not a function of small r, which is the variable over which we are integrating, outside the integration function, right? So let's do that. So I have lambda over 1 minus e to the power minus lambda capital R. Careful that, in the denominator we have capital R. Capital R is fixed, so the radius of the city is fixed, right? So integration 0 to R, R to the power minus lambda R dr. This is something we did in the last lecture, so we are going to do it slightly quickly. So you can look at the last lecture and follow through with this integration. This is done by applying integration by parts, right? So we designate first and second functions, so we rank them. And we know that integration by parts is nothing but if you have an integral with a function of r times a function of g, function f of r, function g of r multiplied with each other, and you must integrate them with respect to r. What you have is f of r gr dr minus integral del f by del r multiplied by integral gr dr whole thing integrated with respect to r. Okay, so I'm going to simply apply this formula here. Okay, so I have lambda over 1 minus exponential minus lambda r sitting outside. So I have r sitting as is e to the power minus lambda r integrated with respect to r. So I have the following evaluated between 0 and r minus integral del r by del r is just 1 times e to the power minus lambda r over minus lambda dr. Okay, so this is the second component, and I'm going to just keep solving this. Okay, so I'm going to take it to the next page as is. I'm going to try my best. So we have, okay, so we have R bar equals, okay, I'm gonna go to the previous page a little bit and follow through. So I have 1 minus, sorry, I made a mistake here. So I think this R was supposed to be inside here. So this R is inside here. So you have a capital R. So you have a capital R here, is 0 sitting out here. So this becomes simpler. Sorry about the fumble. So you have lambda over 1 minus e to the power minus lambda r times r times e to the power minus lambda r over minus lambda, minus just is 0. So that's the first component. Minus the second component is going to look like the following: e to the power minus lambda r over lambda squared minus e to the power minus lambda into 0 over lambda squared. Okay, so I have basically R bar given as lambda over 1 minus exponential to the power minus lambda r times, we are going to have 1 minus exponential minus lambda r 1 plus lambda r over lambda, which can be further simplified. So R bar can be further simplified as 1 over lambda minus r e to the power minus lambda capital R divided by 1 minus e to the power minus lambda r. And this representation is particularly useful because if you recall from the previous lecture, for an exponential distribution with infinite radius, when r was capital, capital R was infinity, the exponential distribution would have given me a mean value which is exactly equal to 1 over lambda. This is something that we saw last time. And now what happens when r is a positive, r is a finite positive value, I have 1 over lambda minus an entity which is given as what you see on your screen. And this entity is going to be a positive number. So what I'm saying is that the mean distance with a finite radius city is going to be smaller than the mean distance that we see with infinite for an infinite radius city, which makes sense. That means that, when I have an infinite radius city, I'm going to have a larger mean distance than if I were to have a slightly lower, sort of finite sort of city, which is only as big enough, right? Right. So of course, so an exercise that naturally follows, an exercise that naturally follows is to evaluate or analyze the relationship between R bar and this finite radius of the city R. Okay, so now I'm going to sort of ask you to stop for 5 minutes and evaluate this relationship. Okay, so I want you to stop for 5 minutes. Okay, stop for 5 minutes. You can pause this video for 5 minutes and evaluate this value, and then we'll come back and then we will resolve the matter. Okay, welcome back from the break. We had given ourselves an exercise to evaluate R bar, that is the mean distance, first moment of our spatial exponential distribution interpretation. We wanted to see how this R bar would depend on the finiteness of the city. So this capital R, if it goes to infinity, well, that's an infinite city, that's an infinitely large linear city. And as soon as you restrict it to, let's say, 100 kilometers, 150 kilometers, I mean, you have a more realistic situation. But from the perspective or point of view of a spatial distribution, it's a finite city that we are trying to model. So we wanted to understand how would R bar depend on capital R. What you see on your screen is a plot of the R bar value as we change the value R. And that one thing that we have discussed, there are two variables in this distribution. One is lambda, which is the rate of occurrence of location markers in the city. The second is the extent of the city itself, which is capital R. So what do? I can fix the value of lambda. I can vary R, right? So I can fix lambda. Let's say lambda is fixed at 0.1, right? Then I can vary the value of capital R. Let's say we can go from 10 kilometers to 20 kilometers to 30 kilometers to 40 to 50 to 60 and all the way, let's say we go to 200. So we have these 20 unique value of capital R, and what we can do is we can simply sort of, throw in or fill in R bar given the formula that we derived in the before the break, right? So we can do that. So we can get R bar from the formula that we derived in the previous, on the previous slide, and then we can plot them, right? I mean, we have R bar on the y axis, we have R on the x axis, and we can see the relationship. Okay, that's one way of doing it. The other way is that I have a mathematical relationship between R bar and capital R. So I have R bar as a function of R lambda, and it's an exponential form and everything that we saw in the previous slide. But we can simply we can say alternatively we can simply derive del R bar by del R, which automatically by definition restricts d lambda equal to 0. So lambda is kept fixed, which I was doing manually when I was doing it on Excel, numerically drawing the plot. But I can do it using a the differentiation operator. And then I can sort of understand whether I find del R bar by del R to be a positive entity, a negative entity, or maybe even 0. Maybe there's no change when R value changes. What do we see in the graph? We see that when we fix lambda as at 0.1, so there is no change in lambda value as we change the capital R value on the x-axis. Lambda is kept fixed at 0.1. R bar seems to be increasing according to the yellow line, which looks like an exponential, inverse of an exponential increase, right? So the increase, there is R bar is increasing in R, but at a decreasing rate. Okay, and it is more clear as you move to a higher value of lambda. Let's say we move to lambda equals 0.5. From lambda equals 0.1 to lambda equals 0.5, you see that R bar still increases as R goes up, but after a certain level, let's say around 11 kilometers, the change in R bar tends to be almost 0, right? So it attains a maximum value of 2, right? And then it sort of, goes to 0. So it doesn't matter whether my city is, 11 kilometers big, or has a radius of 20 kilometers or 200 kilometers, the average distance at which a location marker may be found, or a distance at which I will on average I can expect to see a location marker will be 2 kilometers. That's the physical interpretation of this exponential distribution based relationship between R bar and R. So what have we done till now? We have adapted the exponential distribution, which models time between independently and regularly occurring events, to a spatial domain, right? So now our adapted interpretation of this exponential distribution is to observe location markers away from origin for a linear city of a finite radius capital R. Right? So we have first adapted that. Second, in the definition of this exponential distribution, it's slightly different from what it was in the traditional case of time, time between events interpretation. We had a new parameter called k. We evaluated what this k was. We analyzed what k was. And as a third step, what we have done is we have evaluated the first moment of this spatial spatial exponential distribution. So what is the next step? The next step is obviously the second moment, but now we will study second moment, that is the variation through entropy. So once we have a spatially delineated, a distance-based exponential distribution, we are going to now, as the next step, which I'm going to call as step 3, figure out what is spatial entropy for this example of a linear city having radius capital R and the probability of observing location markers at distance small r from origin given as PR equals lambda over 1 minus exponential minus lambda capital R times exponential minus lambda r. Okay. Now I have a spatial exponential distribution, spatially delineated, where distance, space, right? We studied distance is the most fundamental entity of understanding, or characterizing phenomena over space. So now we have a distribution which is, characterized by that distance, and distance goes from origin, and we know that this radius, this distance r, can only go as far as the maximum radius of this linear city under consideration. So then, what would be spatial entropy? Well, it will be capital E equals minus integration goes from 0 to r PR times log of PR. This definition we have studied in the previous lecture. I'm just writing it again, right? And all right, so once we know that, we can then expand it by putting the value of PR that we have figured out in this lecture. So we have 0 to r with a negative sign, right? K, which is lambda over 1 minus exponential minus lambda capital R times exponential minus lambda small r multiplied by the log of this entire entity. So log lambda 1 minus exponential lambda r dr. Okay. So now what is this entropy a function of? So first of all, it again depends on lambda, but lambda is the rate of occurrence. It's distribution parameter. But the other more critical thing that it depends on is the size of the city, the maximum radius that we provide for studying this city. So we say this entropy being a function of r, we call it ER. We call it ER. Okay, and we can show this ER. It has a little bit of a complicated mathematical formulation, but it has a very interesting physical formulation. So that is something that we'll see now. It is 1 plus log 1 over lambda plus log 1 minus e to the power minus lambda r minus lambda r e to the power minus lambda r over 1 minus lambda r. Now, pay attention to these components with little bit of caution, with little bit of attention. So let's see. So in the green square bracket, I have a term which is quite complicated, right? It is log of 1 minus exponential minus lambda r minus lambda r exponential minus lambda r over a complicated denominator. But what's outside this green bracket is 1 over log 1 over lambda. So 1 over lambda, if you remember, is exactly equal to the standard deviation of a exponential distribution when r could go to infinity. So if capital R were infinity, what we are looking at here is that the first term is equal to 1 plus log of st, which is nothing but e with r, capital R, being set to infinity. So what I am looking at is the entropy of, you know, of a linear city, which can be written as the entropy of an infinitely large city plus an entity, which is a function again of lambda and r, right? So every time, I mean, there is a recurring pattern here that, you know, the functional understanding of how different moments for the spatial distribution depends is critically this radius of the monocentric city that we are looking at. So I'm just going to say that, you know, if you feel confused about this E infinity, well, you can always go back to the previous lecture, and so we can say we showed this in the previous lecture for an exponential distribution. Okay, and it turns out, as a pointer, as a note, I'm just going to say that it turns out that E infinity, which is the entropy of an infinitely large linear city, is less than or equal to this finitely sized monocentric city. The center obviously is the, you know, it obviously has an origin, and it has a finite radius, capital R. Okay, so the entropy, the variation of how, you know, these location markers would be observed over space would be higher, you know, in a finite space than if my constraint of the size of the city was relaxed and it was allowed to expand infinitely. Okay, so the entropy of a smaller city with sort of equal content, sort of equal number of markers to appear over space, the variation at which you are going to see these markers will be realized at a higher level than if the city was larger. Okay, so we right away get an interpretation of what to expect for things like population density, for real estate prices in a large city versus a small city, given that lambda is held constant, right? So here lambda you can think of is a control parameter of, you know, how frequently can you see a marker. So what's the interpretation in the real world? Well, you can think of it as the level of economic activity, right? As the total population that I expect in the city. So if it's a city of a 2 million population, and if we change the size of the city, how will the entropy change? So it's kind of logical to think I'm going to fit a lot of stuff, lot of content in a smaller space. I probably will see a lot of kind of higher variation. All right. So as a next step, we will define. So till now we have. Before we go to the next step, I mean, we have ER, we have a formulation for ER. We know that ER is E infinity plus some stuff, okay? And this some stuff is a function of lambda and R, all right? We understand that now. Okay, so now, as a next step, I'm going to call it step 4, we are going to define the difference between entropy levels at finite radius R and with R approaching infinity. So I'm just saying E difference, E diff equals ER minus E infinity, which clearly from the first equation that I've written is nothing but some stuff, right? This some stuff which is a function of lambda and R. So if I were to go on to the previous slide, I can actually write down the formulation of this remainder, which is a function of lambda and R, and it will come out to be lambda e to the power minus lambda R times R divided by 1 minus to the power minus lambda R minus log 1 minus lambda R. Okay. What is this difference really capturing? It is the distance of variation. Okay, now the second moment, how different is the variation captured by an infinitely large city and a city which has a finite radius R. So it's the difference in the second moment measure for a finite city relative to a infinitely large city. And I had said that E infinity is usually lesser than ER, and we also sort of covered, we just covered a physical interpretation of the same. You can show that del E diff by del R. So whenever I do this, whenever I use the differential operator, what I'm doing is I am fixing the other parameter, which is lambda, right? So I'm trying to create an understanding of what is the impact of this capital radius R, and it turns out that this is less than 0. So that means as I increase the size of my city, I get closer and closer to the entropy levels of an infinitely large city. Okay, and what is going to be interesting for us as a next step, right? So I'm going to say step 5 and I'm going to cover it in 2 minutes. But what is going to be interesting is the proportion of variation or variability captured by a finite city, finitely sized city relative to an infinitely sized city, infinite radius city. So what I'm going to be interested in going forward is to figure out this proportion ER minus E infinity divided by ER. Okay, so I'm normalizing for the level of ER. So I need to sort of create a percentage or a proportion to be able to normalize for the level of entropy that I'm studying. So if I have a city which is 50 kilometers wide from the origin, then I want to sort of make sure that when I'm comparing that with a 100-kilometer city, I'm not comparing apples and oranges. I'm creating a proportion to normalize this difference by the level of entropy that I began with. Okay, so I'm trying to see what is the extent or what's the distance between the entropy that I would get if I had all the space I wanted versus if I have a smaller space, right? What would be an optimal size or appropriate size of a city if I wanted most of the stuff, most of the distribution in population, the way population is spread out, the prices are spread out and all that, if I had no space constraint whatsoever, right? So this sort of comes closer to some kind of a regional policy or regional planning exercise where policymakers might want to understand where should they draw a boundary of a city, right? Where should we stop National Capital Territory of Delhi? Where should we stop, a coastal city like Mumbai, which can only expand in one direction, right? So this idea of spatial entropy and this metric, E diff by ER specifically provides a policy instrument to do that. Before I move forward in that direction, what I'm going to do is I'm going to look at E diff this difference and ER a little bit more closely. So let's go and do that. So first of all, I'm looking at ER. So sorry about the notational goof up. These are all E sub R plotted as a function of capital R. So this is the entropy captured as I increase the size of the city. So the entropy captured goes up as we increase the size of the city, whereas this difference sort of comes down. So del E diff by del R, as I said, will be a negative entity, right? So this is nothing but del E diff by del R less than 0 entity, right? So what it shows me is that as I increase the size of the city, the difference between what would be the variation in an infinitely large city, how would it start to fall down? And of course, you again see either an exponential functions shape when you see these curves, or you see the inverse of it, right? So the shape is all determined by the analytical functional form of the distribution that we began with. So if we begin with a different distribution, let's say we began with a normal distribution, a truncated normal distribution, a Poisson distribution, right, a beta distribution, then all of these results will automatically change according to how the different parameters of those distributions behave or lend to the behavior of the distribution itself. Okay, so having said that, we have understood E sub R, E difference. Now we wanted to understand a little bit more about this proportion H diff or E diff over ER to be able to understand an appropriate size of a city. So it turns out that I have a functional form for the E diff, which is a difference between a finitely sized linear city and an infinitely sized linear city, and the entropies between the two, normalized by the level of entropy for this finitely sized city. And I had said, we have both of these, the numerator as well as denominator. They are both functions of lambda and R, right? We basically want to understand how close is a finitely sized city is to a infinitely sized city in terms of the variation of a given interest, metric of interest, if we change the radius of the city itself. So if we expand the city, how much closer am I going to get to to an infinitely large city as well? So I'm going to call this step 5, and in this step 5, I'm going to set this ratio equals 0.05 or 5%. So this allows for the difference between the infinitely large city and the finite city to be only 5%. So that means that I am looking at a situation, a setting where linear city with radius capital R captures 95% variation relative to an infinitely large monocentric city. Okay, so what can I do going forward? Okay, so I have basically a function of lambda and R, and I'm setting it to be 0.05. What I can really do is that I can actually set lambda. Let me set lambda equals 0.1. And then I can take an inverse of this function and I can figure out the value of R, which is the radius. I can back out the radius of a city. That will capture 95% of variation as far as the entropy is concerned relative to an infinitely large city. Okay, so if I can attain this radius, if I can attain this radius given the lambda value, I can achieve all the variation I want if I had no constraint of space. So constraint of space by itself can be realistically given some kind of a boundedness, right? So it may not be a very large constraint. So if R 0.95 or R 95% turns out to be a realistic value, let's say within 100 kilometers, 200 kilometers, well, we can realistically build such a city which we think will encompass all economic activity, living standards, as far as if they are considered as random variables, to be able to be contained within that city, right? So this will be nothing but L inverse of 0.05 being with lambda set as 0.1. Okay, and we can we can figure that out with a graph. So here again I have E diff by ER, E diff by ER, and I'm going to focus on with the case where I fix lambda equals 0.1. Okay, so let me fix lambda to be equal to 0.1, and I'm going to look at the yellow line, and what I see here is, if you look at E diff by E sub R, E diff by ER, it is actually falling beyond a given distance from the origin, and this value keeps falling and comes to this point of 0.05, which is the value of my interest, at a distance of around 33 kilometers. So R 95% or 0.95 turns out to be 33 kilometers. What this means is that given lambda equals 0.1, the distance from origin equals 33 kilometers is considered an appropriate regional boundary for a monocentric city, right? And what is the definition of this appropriateness of this regional boundary? That it is able to capture 95% of the variation, right? Of course, with lambda values being different, if lambda goes up, you see that R 0.95 is drastically smaller, right? So a lot can be done, with smaller cities as well. So that it's not all is lost with smaller towns and cities, right? But if lambda is smaller, you are going to expect, you can expect a higher, sort of a larger distance or requirement of a larger, spatial scope of a city to be able to, encompass the variation that one would like, right? So this is for the case where probably lambda will be much less than 0.1. Right. So the idea is that, schematically, if you see, I start at the origin, my R stops here, the R could go till infinity, but the idea is that, there comes a value of capital R at 33 kilometers where, ER is actually 0.95, which is 95% of E infinity. Okay. Now, as an exercise, I'm going to sort of ask you to figure out the radius of a monocentric city that captures 99% of the variation. So I'm going to make it stricter. So I'm going to say figure out R 0.99 such that E diff by ER equals 0.01, you can set lambda equals 0.1, right? And you should figure out what for R 0.99 is, in the next 3 minutes. Okay, so I will tell you R after I discuss this little schematic in front of us, so what we are looking at here are different cities, a spatial map of different cities, including Jakarta, Paris, Moscow, Shanghai, Berlin, New York, and London. And what you see, interestingly, is that many of these cities, if not all, actually have something like a center. And around this center, the city sort of distributes itself in a way that could be explained as an exponential decline in, let's say, population density or trade, some kind of economic activity, maybe groundwater depletion, right? You might see a lot of depletion around the center, and then that might actually becomes better as you move away from the city into the heartlands, right? So you see a similar shape for Shanghai. Of course, the axis at which you want to analyze these things can be different. But the model that we are studying here can be useful to understand or characterize the spatial spread of real-world cities. Coming back to the question, well, the value of R 0.99, where if you wanted to capture 99% entropy, which I had set for you a minute ago, well, it's going to be 53 kilometers. So interestingly, while R 0.95 was 33 kilometers, you would have to go out 20 kilometers more, which is a lot of space if you think about it on land, if you were to go from 95% to 99%, variation of a city. So that's about it. I hope you enjoyed this exposition of spatial entropy, use of spatial entropy for regional planning, to understand, characterize cities around us. Thank you very much for this lecture.